Let's suppose that we have a set of data points, and we want to find a line that approximates those data points as well as possible. So we're trying to find a line of best fit. One way that we can see just how well a line fits a data point is by taking the sum of squares, meaning we take the y-coordinate of the data point minus the predicted value by the line, and then we square that distance. And then we add up all those. And what we want to try to do is we want to find the line where the sum of those squared distances is as small as possible. So this is the least squares problem. And the formula for the sums of those squares is the sum over all our data points of yi minus mxi plus b. That's the y-coordinate minus the predicted value. And then we square that for each one. So I've just distributed a negative sign here. And what we notice is that this is a function of only two variables. There's a whole bunch of arbitrary constants, yi and xi, but those are just given to us by our data sets. And what we're trying to optimize isn't those points, but is the slope and intercept of the line we're trying to find. So if we want to find the m and b that minimize least squares, or that minimize the squares, we want to find the critical points of D. So that might seem intimidating, but it's not as quite as bad as it looks. So we want to find where each partial equals 0. So we're going to find where the gradient of D equals 0, 0. The gradient, or the partial derivative in respect to m, well, one thing we know about derivatives is that we can take the derivative term by term. So what that means when we have this giant sum is that I can basically just ignore the sum and just take the derivative of an arbitrary term. So what's the derivative of this going to be in respect to m? Well, I can use the chain rule. That's going to be 2 times yi minus mxi minus b. Then multiply by the derivative of the inside in respect to m. That's going to be times negative xi. Or that will be the sum of negative 2xi times yi minus mxi minus b. Similarly, for the partial in respect to b, we'll use a similar trick. That's going to be the sum of 2 times, oh, no xi here, 2 times yi minus mxi minus b times the derivative of the inside in respect to b. That's just -1, so I'll just put a negative sign out there. And what we want to do is we want to set each of those partial derivatives equal to 0. And while that might seem intimidating, due to some algebra shenanigans and breaking up our sums into different parts, we can actually rewrite these equations relatively simply. So that first equation is going to become, we want the sum of all the x values, the squares of all the x values, times m, plus the sum of all the x values, times b. We want that to equal the sum of all the x values times all the y values. And we want the other one, our partial in respect to b equaling 0. That's going to turn into the equation. We want the sum of all the xi's times m plus the number of points we have, n times b, to equal the sum of our yi's. And while that might look gross, let's note that this is a constant, this is a constant, this is a constant, this is a constant, this is just n, and that's a constant. So this is just a regular system of linear equations that you can solve. And when you solve that system of linear equations, you get a beautiful, simple result where you want your m value to be n times the sum of the xi, yi's minus the sum of the xi's times the sum of the yi's. All of that over n times the sum of the xi squared minus the sum of the xi's, all of that squared. So that's your m, and your b value is going to be the sum of the xi's squared times the sum of the yi's minus the sum of the xi's times the sum of the xi's times the yi's, all of that over n times the sum of the xi's squared minus the sum of the xi's squared. And would you guess, thanks to things like the Hessian criteria and stuff, we actually find this is a minimum. So all we really knew is that it was a critical point, but we can add on the point that this is a minimum, which is good news. It would have been a real bummer if we'd done all that work and found like the maximum of the least squares, which would be unhelpful. So in all that, we got these formulas basically just using what we know about optimizing multivariable functions. And we can use those formulas to find the line of least squares, but we'll do that in a separate video.